Hello everyone, my name is Rajam Khurshi and I'll be taking this live session for NPTEL course on operating system fundamentals. So I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. This is an extra class and we'll be solving some problems related to some miscellaneous problems related to the operating system problems which we have covered previously, some extra topics. So as usual, the class will be interactive. Please feel free to ask any question as and when you need any help. So let's begin. So let's start with this question. So let's come to this first question. It says that we have a processor which uses 36 bit physical addresses and 32-bit virtual addresses. 32-bit physical address and 32-bit virtual address. And with a page frame size of 4 KB. So the page frame size is 4 KB. A three-level page table is used for virtual to physical address translation, where virtual address is used as bits 30 to 31 is used to index the first level page table, bits 21 to 29 are used to index the second level page table, and bits 12 to 20 are used to index the third level page table, and bits 0 to 11 are used as an offset within the page. What is the number of bits required for addressing the next level page table in the page table entry of the first, second, and third page tables respectively? So it is a big question. So let's get to it one by one. So it says, so previously we have gone through the concept of multi-level page table. So we have gone through the concept of multi-level paging. So why we are doing multi-level paging? If you remember, the reason we are doing multi-level paging is because the size of uh, holding the entire page table in memory is difficult. So we have seen that holding the entire like the virtual size of the memory is always very big. You know that the actual memory is much bigger than your physical addresses. Now storing the entire page table inside the main memory has been found to be very difficult. So what does your page table store? Page table stores the why is page table is required? Page table is required to translate your main memory address, your physical address to your virtual address, right? So to your virtual address to your physical address, right? That translation you need. So like it tells you where in the physical memory it is present or not. So if it is present in the main memory, you can directly go to the main memory and fetch it, or if it is not present in the main memory, you have to fetch it from the secondary memory to the main memory and then use it, right? So we have seen the scenario that it is difficult to keep the entire page table in the main memory. So that's the one of the reason that we use multi-level page table. What happens in a multi-level page table, where the the first level of the page table is actually in the main memory, is actually in the main memory, and the rest uh, and each entry of this first level page table uh, is is basically points to another page table, is another basically points to another page table. So in each entry in the first level page table basically points to another page table, and those page table may or may not be present in the main memory. So so as and when required, we take it from the secondary memory and use it. So that is the that is what your multi-level page table is. So always remember, your first level of the page table will always be in the main memory. It has to be in the main memory, but the rest of the level uh, maybe outside the main memory. Okay, so in this question, what it says, there is a 36 bit 36 bit physical address, 36 bits physical address, and a 32-bit virtual address. Let me just redraw it. And a 32-bit virtual address, right? Of this virtual address, so what is the job of your page table? To translate this virtual address into physical address, right? So what it says is that, so what it says is that here it is divided into four parts, right? So this is your these bits, these two bits, that is 31 to 30. These bits represents your first level. This represents your second level, that is your 21. So if you this 0, 11, uh, 20, 29. So this represents your second level, this represents your third level, and this represents your offset. So in this way you can divide your in this way you can divide your entire physical address, right? Virtual address. So that is what it is says. Now note one thing. So the offset is 12, right? So so uh, so let's start solving this problem. So the question is, how many number of bits, the number of bits are required. So the question arises is the number of bits required for addressing the next level page table in the page table entry of the first, second, and third level page table. So how many bits are required? So how many of these bits are required to address the next level page table in the of the first level, third level, and second level page tables? So always remember one thing. Uh, Always remember one thing. Your third level, or let's say last level page table is the one that translates virtual address to physical address, right? So that is the one that translates your virtual address to physical address. That translates virtual address to physical address, right? So how many bits are required for that, to represent that? So as you can see, so as you can see uh, so you have a page size of it is given here, your page frame size is 4 KB. So what does that mean, page frame size? So this is your physical memory where each frame is of size 4 KB, right? So, how many? What is 4 KB? So, if you have an address of 32 bit here, so 4 KB is basically your uh, 2 into 2 to the power of 12 byte, right? So, basically, your 12 bits represents your this offset, and the rest of it basically represents the address it basically represents the address part to translate your virtual address to a physical address, right? So what it will be, 36 minus 12 is equal to 24. So 24, not page size. So 24 number of bits required for third level. So number of pages required for third level, uh, for addressing the third level of the page table, for addressing for addressing third level of page table is basically this. Right, so that is the way you will do it. Now the question is number of bits required for address of second level page table. So what does the second level page table refers to? The second level of the page table basically refers to, let's say this one is this. So refers to this. So it points to each entry of a page table in the third level. So it basically points to each level, each table in the third level, right? So number of entries. So number of third level. So we need to calculate first number of third level page tables. So we need to calculate that first. So what is the physical memory we have? Number of third level page table. So number of we have the physical memory as 2 to the power of 36, right? And divided by size of a third level page table. What is the size of a third level page table? Right. Uh, let me write the equation. Number of third level page table is basically physical memory size divided by size of third level page. So that comes down to physical memory size is basically 2 to the power of 36, and the size of a third level page is size of a single third level number of entries in a single third level page, that is 2 to the power of 24, right, into the number of bits required. So if you have seen, so number of bits for the third level page is 9. So that will be 2 to the power of 9. So that will be 2 to the power of 9. And size of each page table is basically 4. let me rewrite it. So here we have physical total physical memory size is to the power 36. So we are calculating number of third level page table. So number of third level page table will be physical memory size divided by size of a third level page table. So size of a third level page table will be what? Number of entries in a single third level page multiply by size of an entry. Size of an entry. So that will come down to 2 to the power of 36 and number of entries in a single third level page, that is basically that indicates basically this part bits required to use the third level page, that is the nine bits are required. So each entry will be have so each page table entry will have 9 bits, 2 to the power of 9, and size of each entry is basically how much is basically your size of each entry is how much is basically 2 to the power is 4, right? It's 4 kb, it is given because each page, it is actually each page. So that comes down to, if you calculate this, it will come down to 2 to the power of 25. So 25 bits are required to address a so 2 to the power 25, 2 to the power 25 third level page tables are possible. So that 25 will be the number of bits required for addressing a third level page table. So that will be 25. So first one for third level page table, it is 24. This one is 25, 24, 25, and this one will also come down to the size divided by it. So that is basically the size of the physical memory, that is 2 to the power of 36 divided by number of bits, that is 2 to the power of 9 into 4. So it will also come down to 25. 2 to the power 25, that is 25 bits are required. So all the three, this one will require 25. First level page table addressing will 25. Second level page table will require 25, and third level page table will require 24. That will be the answer. So okay. Let me explain it again. Okay. So I know it is a little bit confusing. So let me do it again. So what we have been given is a physical memory. Physical address is 36 bit. So your physical memory is basically 2 to the power of 36. Physical memory is 2 to the power of 36. Right. Now your virtual address is basically a 32 bit, where first two bits, the first 0 to 11 is your offset. Next 11 to 12 to 19, and that is 12 to 20 is your first level, second level, and third level, right? That is your third level, second level, and first level. Uh, 29, 31. First, second, third. Right. So first task is to calculate. So what does third level page table does? It stores all possible pages corresponding to the size of main memory. So if the size of the main memory, so how many entries will be there? So total size of the main memory is 2 to the power of 36. Now, how many frames or pages are possible? How many pages are possible? You have been given the page size. Page size is given as page size is 4 KB. So total how many pages possible in the main memory? So this will come down to 2 to the power of 12. Right, 2 to the power of 12, it will come down to 2 to the power of 24. So that is the total number of pages. Total number of pages. Right. So third level will always do the translation for contain the address for all of them. So 24 bits are required for addressing third level page table. Now we need to calculate total number of third level page table. Right, that is stored in the main memory at this point of time. So total number of third level page table will be basically the 2 to the power 36. That is your total main memory size divided by size of each page table entry. So each page table entry, we know that these bits, the 2 to 12, represents the third level page table number of bits. So that is 2 to the power of 9 bits, right? And size of each page table entry. So size of each page table entry, is it given? See, it is given. Size of each page table entry is of 4 bytes, right? So it will be 4. So total number of third level page tables will be, so this is size of each page table entry, size of each page table, and this is the number of entries in each page table, and the size of each entry. So number of third level page table is basically 2 to the power of this will come down to 2 to the power of 25. So that is the number of third level page table entry. So number of third level page table entry is basically what and each will be addressed by your second level page table. So 25 bit of addressing for second level page table. And if you calculate it back for first level, it will also come down to 25. So the correct answer is uh, 25, 25, and 24. That is your correct answer. Okay, so let's do a similar kind of problem to understand more in details this concept of multi-level page table and what is the page size in the entries, right? So consider this. So a computer uses for 36-bit virtual address, 32-bit physical address, and a 3-level page table organization. The page table base register stores the base address of the page table T1, which is exactly one page. So it says that T1, the base level page table, is basically one page, and it is logical because you want the minimum amount of pages in your first level. So it is logical and it is totally present in your normal systems that at first level you have only one page table and whose size is basically your size of one page. So T1 is has one page table, and each entry of T1. So T1's each entry uh, stores the base address of second level page table. So there are many second level page table, T2 dash, T2 1 dash, T2 double dash. So there are many page table, and each entry is stored here. Then each entry of T2 holds many third level entry, right? That is what it does. Now each entry of T3 page stores a page table entry. So now each entry of T3 stores a page table entry of has stores a page table entry. Now PT size is 32 in size. So each page table entry size is 32 bit. Size of PT is 32 bit. 32 bit, which you can call it as basically 32 bit is basically how much KB is 4 KB, right? So what is the size of page in KB in this computer? So the question is, what is the size of page in KB in this computer? Okay, so let's assume, let's do this like this way. So let's assume the size of a page is size of pages x. Okay, now since virtual address is 46 bits, so total number of pages is total number of pages. So your total size is, so virtual address is to the power of 46. That is your total size of your virtual memory divided by each page size. That is x, right? Now we should have a entry of each page in the last page table. So as we saw in the last example that each entry of a third level page table must point to one of the pages, right? Because that's the way your translation is happening. So now total number of, so that means total number of entries in all T3 uh, in all T3 page tables is basically 2 to the power of 46 divided by x. Now we know size of size of each page table entry, size of each page is basically 4 bytes, right? So we defined here, so that 32 bit is 4 bytes. So size of each page table entry is 4 bytes, right? So it will come down to then, so this is the total number of entries in all PTE. Now total size of entire T3 tables is basically this total number of entries 2 to the power 46 divided by x into 4b, right? So that is 2 to the power of 52 by x. That is the total number of entries, total size of entries in T3. right? So now this entire T3 will be converted into your is equivalent to your like, so these are the total number of entries. Now we need to find out total number of T3 tables, right? So what it will be? So that will be equivalent to one page. So 2 to the power of 52 divided by x, because one page is one table, right? Size of each table is basically one page. So 2 to the power of 52 divided by x square. So that is the total number of T3 tables, and that will be what is that? That is basically equal to total number of entries in T2 table, right? So we have total number of entries in all this, and now total number of entries in this is this 2 to the 52 divided by x square. So if we continue like this, so we'll again continue like that. So total size of all entries in T2 is basically 2 to the power of 52 divided by x square into 4, because this is the total entries in T2, and this is size of each entry. So this will come down to 2 to the power of 54 divided by x square. Now number of total number of T2 tables is basically 2 to the power of 54 divided by x square divided by x to the power of 54 divided by x cube, right? And this is what, sorry, this multiplied by 4, it happens to be 2 to the power of 50, 2 to the power of 50, 2 to the power of 50, and this multiplied by 2 is 2 to the power of 52. Now this is the total number of entries in total number of T2 tables. That is the total number of, that is your total number of entries in T1, right? No, that I made another mistake. So this into 2 is 48. It's basically 48. 48, 48, 48, 50, 50, right? That is the total number of entries in T1. So total number of entries. So size of, so therefore size of T1 is basically 2 to the power of 50 divided by x cube into 4, because each entry is again 4 bytes, so that will come down to 2 to the power of 52 divided by x cube. Now if this is the size of the T1, we all know size of T1 is basically size of one page, so this should be equal to x. So this is our equation. So, or if we solve, x to the power of 4 is 2 to the power of 52, or x is equal to 2 to the power of 13. So x value is 2 to the power, so that is 8 kb. So the correct answer is 8 kb. So size of each page is basically 8 kb. Right. So that is how we do it. So if I do a small recap about what we have done is, so what we have told is there is one T1 at T1, that is total one page, and that is the first level entry. Then you have T2, where each entry of T1 points to one table in T2. Then there you have T3, that each entry of T2 table points to one T3 table, and so on. Now we have been given a 46-bit virtual address space. The total number of pages will be how much? 2 to the power of 46 divided by x. Then we calculate the number of entries is T3 is basically this. The total size of the T3 table is multiplied by 4. Number of T3 table is basically size of each table is basically x. So 2 to the power of 48 by x is this the total number of T3 tables. That is the total number of entries in T2 table. So we continued like that, and ultimately we find out that size of one entry is basically a page size, and that is the value we derive calculating backwards. So size is basically 8 kb. Okay, so let's come to the next question. So the question is, you have been given a virtual page reference. So you have been given this virtual page reference of 1, 2, 3, 2, 4, 1, 3, 2, 4, 1. And we will be using the LRU, optimal, and FIFO denote the number of page replacement. So what is the page faults for each? So which of the options will be correct? So if you are using LRU, least recently used, so it's a page size of 3. So initially one will come, no fault, one fault. Two will come, another fault. Three will come, another fault, another fault. Then least recently used. So the next will come is 2. So 2 is already present, so no issues. So it will remain 1, 2, 3. Then 4 comes. Uh, sorry, so this one will not be there. Okay, so this done. So now 4 comes. Now 4 is not present, so 1 has to be replaced. So which one is the least recently used? So the least recently used is 1. This is 1. So 1 will be replaced. 4, 2, 3. Now the which one is the least recently used? After that 1 comes. Now the least recently used is 3. So 3 will be replaced. 4, 2, 1. Then 2 is already present, 4 is already present, 1 is already present. So for LRU, we have 5 page faults. Now let's use FIFO. So FIFO will be have uh, your traditional, it will be same, 1, 2, 3. Then 2 is already present, no issue. Now 4 comes. So we will replace 1 because that one was the first in first out. So that will be replaced. 4, 2, 3. Then 1 comes. Then 2 will be replaced. 4, 1, 3. 3 is already present. Then 2 will be then 2 comes. 4 will be replaced because which one will be replaced when this comes 2. So the last one was that 3. So she will be replaced 4, 1, 2, and less dollar present. So for P4 it is 6. Now if you use optimal, it will be, let's do it. 1 is there, 1, 2 is there, 1, 2, 3 is there. Now when 4 comes, we will check which one will be the uh, is the farthest to you be used again. So we see 1 and 3 will be used again, but 2 will be the one that will be again used later. So we'll release 2, 1, 4, 3. This gone, then 2 comes. So we will replace 3, 1, 4, 2. So is 5. So correct one is this. Optimal is equal to LRU. Okay, so let's go to the next one. So you have been given a paging hardware with TLB. Okay, so you have been given a paging hardware with a TLB. Now assume the entire page table and all pages in the physical memory. It takes 10 milliseconds to search the TLB. So searching the TLB, it takes 10 milliseconds and 80 milliseconds to access the physical memory. If TLB hit is 0.6, then the effective memory access time is so TLB hit is 0.6. So we know EAT, estimated access time, is basically 0.6. That is the hit time, hit rate into so if it is a TLB hit, so what it will do, it will search the TLB for the address and then address the miss memory, right? That it will do. But if it is a TLB miss, what it will do, so it will search the TLB for 10 milliseconds and then it will search the page table and also the frame for the translation. So it will come out to be 0.6 into 90 plus 0.4 into 170, right? So it will be 54 plus 68. That will be 122 ms. Right. So this we have studied in the class that if we have a TLB, what will TLB do? So if there is your uh, so TLB, then there is your page table, and then there is your physical address, a frame. Now TLB is fast, it is a cache. This is in your main memory and this is your main memory. So if a paging hardware, so if your CPU, the OS asks fast checks the TLB. So if TLB is hit, so TLB is hit this case, so it will directly access here. That will take 80 nanoseconds. If TLB is a miss, then it will find access here, then go here, and then go here in this route. So one memory access, two memory access. So it is 2 into 80 plus 10. So it is 120 milliseconds. Right. So this is quite standard. Now let's go to the next one. So consider a 6 memory partitions. So you have a memory partition of 200 KB, 400 KB, 600 KB, 500 KB, 300 KB, and 250 KB. And you have four process sizes. So you have given four process sizes: 357 KB, 210 KB, 468 KB, and 491 KB. So if we are using best fit algorithm, which partitions are not allotted to any process? So what does this mean? It means that you have been given these partitions and you have to fit in these processes. And the question says that we will be using the best fit algorithms, right? Best fit algorithm means the one which leaves the least fragmentation after allocation, right? So if we are using 357, so the best possible one will be 400 KB. So 357 process. So this is your process and this is your partition. So the 357 KB process will be stored in your partition 400 KB, right? Next is your 210 KB partition. 110 KB partition will be stored in your, the closest is basically your 250 KB, 250 KB partition. So, mm, so this gone, this gone. Now you have your 468 KB partition, 468 KB process. It will be stored in your 500 KB partition. It's gone. Now you have your 491 KB partition. 491 KB partition, and only one possible, that is 600 KB. So your 600 KB is also booked. So the remaining ones are 200 KB and this 300 KB. So these two are not allocated to any process. Right. So this is your answer. So best fit we have studied that it will always chooses the one which has your least fragmentation effect. Okay. So let's go to the next one. So this is a very interesting problem, and it is quite commonly asked in many exams. So you have a machine which has 64 MB physical memory and 32-bit virtual address. Now, if page size is 4 KB, page size is 4 KB, what is the approximate size of the page table? Now, your physical memory is 64 MB. So, if we write it properly, it will be 2 to the power of 20 into 2 to the power of 6 bytes, that is 2 to the power of 26 So it is basically 2 to the power of 26 byte. 26 to the power of 26 bytes. Your page size is 4 KB. Virtual addresses, virtual addresses to 32-bit. That is basically, so virtual memory size is 2 to the power of 32. Now, page size is 4 KB. That means 2 to the power of 12 byte, right? Virtual memory is 2 to the power of 32. So first we need to calculate number of pages. Number of pages comes from virtual memory. So 2 to the power of 32 divided by 2 to the power of 12. That is the size of each page. So that is 2 to the power of 20. That is the total number of pages. Now total number of frames. Number of frames is basically 2 to the power of 26 divided by 2 to the power of 12. That is 2 to the power of 14 frames. Now a page table size will be the total number of pages is basically 2 to the power of 20, right? Now, what does the page table contain? A page table, what does the page table do? Page table translates a virtual address to a physical address, right? So, physical address in this case will be the number of bits, number of frames, that is 14 bits. So this will be, so each entry will be basically 14 bits. So page table size will be page table size is basically we are picking up this total number of pages, that is 2 to the power of 20, right? And number of frames, so you require 14 bits for each frame, so is 14. So this will basically come out to be how much? So 14, we can approximate it to, let's say, 16 bits. That will be 2 byte. So it will be 2 MB. So this approximate size of the page table will basically be 2 MB. So it basically boils down to the fact that what else a page table do. So page table basically translates a physical address, virtual address to a physical address. So each page table entry will contain the frame number, right? So what is frame number? A unique identifier for each frame. Total number of frames are there, 2 to the power of 14. So you require 14 bits to represent each frame identifier. So that will be 14 bits for each entry, and number of page tables are, what is the page table? Number of entries in the page table is basically the number of pages. Number of pages is basically 2 to the power of 20. So 2 to the power of 20 into 14, that will be approximately, let's say 14, we take it to 16, so it will be 2 MB. Okay. So this is a very interesting and important concept, and it's get constantly asked that what is the size of a page. Okay, let's go to the next one. So it is kind of a continuation of the previous problem, so so that it will help you to understand. So you have a computer system with page size of with that implements 4 KB pages. So each page is page size. Use a different link. So page size 4 KB, 32-bit physical address, 32-bit physical address. So number of frames is 2 to the power of 32 divided by 4 KB is how much? 4 KB is basically uh, 2 to the power of 12. That is 2 to the power of 20 frames. So each page table entry contains a each page table entry like 4 KB is fine. I didn't had it. So in this case, we need to find out the length of the virtual address space subnet. That will come. So it is given 8 KB. I missed it. 8 KB. So it will be 2 to the power of 19 frames. Now that means 19 bits required to identify each frame, right? So size of each page table entry will basically be this 19 bits identifier plus it says a valid bit, one valid bit plus a dirty bit and plus one dirty bit plus three permissions bit. So that will be 24 bits size of each PTE. Now size of page table is 24 MB. So we need to find out number of page table entries. That will be 24 MB divided by 24 bit. So it will be basically 24 will get cancelled out. So it will be each bit is basically 8. So 8 so it will be 2 to the power of 20 for MB and 2 to the power of 3 plus bit, that will be 2 to the power of 23. So 2 to the power of 23 number of page tables, right? So that is the number of page table entries. So virtual address space will be, so that is the total number of page table entries. So virtual address space will be 2 to the power of 23 into size of each page. Size of each page is that, so each page table entry is basically number of pages that will contain, and size of each page is 8 KB. So it will be 2 to the power of 26 KB. That is basically 2 to the power of 36 bits. So the virtual address space will be supported will be 36 bits. So I will repeat it. I will let me do it. Let me repeat it once again. Let me clear it up and do it again. Okay, that will be a much easier way to do it. So what we have is a page size. So page size is basically 8 KB, 32-bit physical address space. So number of frames will be 2 to the power of 32 divided by this 8 KB. So that is 2 to the power is basically 2 to the power of 13 bits. To the power of 13 bits is to the power of 19. Okay, so you need 19 bits to uniquely identify each frame. So we know the PT, the size of PT page table entry will be 1 for valid bit plus 1 for dirty bit plus 3 for permission bit plus this page identifier, that is 19. So that will come out to be 24 bit. Now maximum size of the page table is given as 24 MB. So total size of the page table is given, size of each PTE we have. So we need to find out number of page table entry, which is basically the number of pages, right? So it will be 24 MB divided by 24 bit. So it will be 24 into 2 to the power of base 20 into 8 divided by 24. So it will come down to 2 to the power of 23 pages, right? 2 to the power of 23 pages. Now total virtual memory will be number of pages multiplied by size of each page, that is 8 KB. So it will be 2 to the power of 36 bytes. So virtual address space number of bits will be number of bits that is required for each will be 2 to the power of it will be 36 bits. So it will be 36 bits. So the answer will be 36 bits. So this question 6 and question 7 are quite related, and these kind of questions are quite always given, like what is the size of the total memory, virtual address space, the number of bits required for each page table entry and all. Okay, so let's go to the next one. So let's consider a system with 40-bit virtual address space and a page size of 16 KB. Okay, if the computer system has one level page table per process and each page table entry requires 48 bits, the size of per process page table is how much? So this concept again comes from the previous one, and we use the concept which we used previously. Okay, so what is given here? We have a virtual address of 40 bit and therefore the size of virtual memory will be to the power of 40 byte, right? Now you have been given a page size of 16 KB, right? So it will come down to 2 to the power of 14 byte, right? So number of pages is basically 2 to the power of 40 divided by 2 to the power of 14 is basically 2 to the power of 26, right? And this is number of page table entry. Now each page table entry requires 48 bits. So size of page table will be 2 to the power of 26 into 2 to the power of into 48 bits. Now so if it is in bits, so if we do it in byte, so it will be divided by 8, so it will come down to 6 into 2 to the power of 26 byte, which will basically, if we calculate it, will be MB will be to the power of 21, so 6 into 64 MB, so that will be 384 MB. So that is your page table size, 384. So again, it comes from the same logic that you have a page table, and each page table entry, each page table entry corresponds to each page of VM, right? Virtual memory, correct? And now what does each page table entry contains? Each page table entry contains frame numbers, right? So each bit to consider a French number is the number of bits that are stored, and plus it can contains some other bits like that we have seen in this problem, that it has some valid bit, dirty bit, permission bit, etc. That may also be present. So the complete package is basically what gives us this whole uh, total page table size. So total page table size will be total number of pages into size of each page table entry. What is the size of each page table entry? Is frankly mostly consist of a number of bits required to represent a frame. So number of bits required to represent a frame. Okay, that is what it shows mostly. So let's go to the next question. So you have been given a process. So you have been given a process executing on an operating system that uses demand paging. Now, the average time for memory access in the system is m units. If the corresponding memory page is available in the memory and d units, uh, uh, the average time for memory access is m units. So let's jot down some things. So average time for memory access in the system is m units, and the corresponding memory page is available in the memory, and if the corresponding memory page is available in the memory, so average time for memory access if it is present in the main memory is m units, and d units if the memory access causes a page fault. If it has been experimentally measured that the average time for memory access in the process is x unit, which of the following is the correct expression for the page fault rate experience? So we need to find the correct expression for the uh, uh, page fault rate. So what we have been given is the average memory. So we know this thing, right? So this is the equation we actually know. So average access time, estimated average access time is basically 1 minus page fault into memory access plus mm, page fault rate into the like if page fault into service time, page fault service time, right? So in this case we have been some variables has been given for each of it, right? So let's do it. So it is given as x, the average access time, and let's say the page fault rate is p. Let page fault rate be p. Okay, so let it be 1 minus p. So there is no page fault. The memory access time is m, right? And if there is page fault, the memory access time is, if there is a page fault, that is p. The rate of page fault is not given. If there is a page fault, the memory access time is d. So we need to find out an expression for p. So we will basically solve this equation to find out the value of p. So let's do it. So x equals to m minus p of m plus p d, or let's take the p common, d minus m is equal to x minus m. So if we continue it, p is equals to x minus m divided by d minus m. That is your uh, equation, the expression that is required to be found out. So let me again just go through it. So we know, so if there is a page fault, what happens if there is a page fault? So what is a page fault? So this is your page table entry and it corresponds to the particular frame where your page is, right? Now, if it is not present here, what we will do, we have to go to your secondary memory and load it into your main memory. So, so if there is no page fault, what happens? So this address is translated and the corresponding frame number, we go to the corresponding frame number to fetch the page, right? Now, if it is not there, what will happen? If it is not there, what we will do is there will be this page fault service routine which will evict a page from here and bring a page here and that process and all. So in normal case, you will directly access the memory if there is a page fault, which is this. When there is no fault, we will directly access the memory. Here it is, that is M units, and we have done that here. No page fault, and if there is a page fault, that is T units, we multiply it by here and do it. Okay, so let's go to the next one. So what we have been given here, the question says we have a disk of 200 tracks. So we have a disk with 200 tracks, 0 to 999. At a given time, it was servicing the request at the given time from track 190, 120, and at the previous request, the service was for track 90. The pending request are 30, 70, 150, this and this. So how many times will the head change its direction for rescheduling SSTF and FCFS? So let's do the FCFS first. So previous request was 90 and it came to 120. So it is going in one direction, right? So in direction, so it is first like CFS. So that means it is going in the direction towards 99. So if this is 0, this is 199. So it is going towards the right, right? So the next will be mm, next will be 122. So if it is FCFS, first come first serve. So first request is 30, 30, then 70, then 115, then 130, then 130, then 110, then 80, sorry, then 80, then 20, then 25, right? So if you look at this, there is change of direction how many times? So here is a change of direction. So it was going upwards, but it has to go down now. Then there is a change of direction because it should from 30 it should go downwards, but we are now going upwards. So upwards go Then here is another downward spiral from 130 to 110. That is another downward spiral that goes. So in total for FCFS, that is three times change of direction. Right. So now let's do the same for SSTF. So you are 90, 120. Now, out of which of them which we will go first? So the nearest is basically 150. So it will go to 115, right? Then nearest to 115 is 110, right? Now, which is closer to 110? Uh, now, which is closer to 110? So 110, its closer is 130. So the options are 130 and 180. So the closest is 110, 130. So it will go that side. Then we all go backward. So it is 80, 70, 30, 25, 20. So in total, there are how many changes? This is one change. This is one change. This is one change. And this is one change. So there are three changes here. Three times change of direction. And in this case, there is one more change of direction. So if you look at, there is another change of direction from 20 to 25. It is again changing the direction upwards. So that is four times change of direction in this case. So for SSTF, you have three times change of direction, and for FCFS, you have four times change of direction. Okay, so the correct answer is four times and three times respectively. Okay, so let's go to the next one. So the question is, you have been given a counting semaphore which was initially initialized to 7, and we do 20p operations, and 20p operations and xp operations are completed on this semaphore. The final value of the semaphore is 5. So what is this? What is counting semaphore? So what is the difference between counting semaphore and binary semaphore? So we know semaphore, that is semaphore are used uh, semaphores are used to for mutual exclusion, right? So when you are using a semaphore like binary semaphore, with value 0 or 1, it is basically a mutex. It is basically a mutex lock. So it is basically a mutex lock. So why it is a mutex lock? So what does so it gives us two operators, P and V. So initially a binary semaphore is initialized to 0. So what does P do? P will reduce the value by 1, and V what will do? It will increase the value by 1. So suppose if the value is initially 0, which is most cases in a binary semaphore, if the value is 0, and if we do a P, so what it does it do? It will really decrease the value to -1, and it will be stopped there, because it means that you cannot go there inside. Someone else is holding the lock, and when you do a V on this, it becomes 1. It increases the value by 1. Now so uh, while your normal binary semaphore is basically gives you the mutex, what does counting semaphore is used for? Counting semaphore, as we have as you recall maybe, so you have a pool of data. Counting semaphore helps you in calculating that how what is the amount of data when the buffer is full or not. Those kind of things it can help. So because that also need to be counted when you are doing it. So counting semaphore is used for that purpose, for keeping a track of the capacity and those kind of things. So in this case, what we have been given is so in this case what we have been given is uh, uh, that the counting semaphore is initially initialized to 7, and then we perform 20 wait operations and x signal operations. So we do 20 p operations and 20 p operations. So if the initial value is 7, then after 20 p operations, what it will be? 7 minus 20, that will be minus 13. Now it is uh, it is said that the final semaphore value is 5. Final semaphore value is 5. So how many signal operations are doing? We are doing XB operations. So that is the reason it increases from minus 13 to 5, right? So number of V operations will be 5 minus 13. The difference between these two numbers, that will be 18. So the value of x will be 18. So we are doing 18. We are doing 18 V operations, V signals. So we will repeat. I will repeat again. So you have your semaphores. So your counting semaphores, not your normal binary semaphores. Counting semaphore, what it does, it continuously increases and decreases the value. So now what happens? In this case, we are doing the counting semaphore was initially initialized to 7. So we are doing 20 p operations. That is 20 times we are decreasing the value of semaphore to 7, and then we are doing x v operations. That is x times we are increasing the value of each time we are increasing the value of v. So and the final value is count out to be 5. So if you are doing 20 p operations on 7, that means you are decreasing the number by 20. So 7 minus 20 is minus 13, right? So now how many v operations we need to do so that the final value is 5, right? So that is basically the difference between the two numbers, minus 13 and minus 5, right? So that is your answer. 5 minus minus 13, 18. Okay, so let's go to the next question. So these questions are for scheduling. So our operating system here. Our operating system here uses a shortest time remaining fast scheduling algorithm. Shortest time remaining fast scheduling algorithm, and with a preemptive scheduling of processes. Preemptive means, what does preemptive means? So it can be swapped out as and when required. So there can be many cases that like it can have a specific burst time up to which it can do, and other than that, you have your priority. Based on priority, it can be preempted out. Those kind of things are there. So let's do this. So we have been given the arrival times of for each. So there are four processes: P1, P2, P3, P4. Arrival time is 0, 2, 3, 8, and you have a specific burst time. Okay, so we will use that concept of Gantt chart. So let's draw it, the Gantt chart. So initially, for the first 2 seconds, so 0 to 2, there are only one process left, that is P1. So P1 will be from 0 to 2. So P1 has a total bus time of 10. So after that, after 2 seconds, it will have only 10 remaining, and we know our concept is shortest remaining time first. So after 2 seconds, when P2 arrives, the shortest remaining time is of P2. So then P2 will be scheduled. So after third, your so after third, your P3 comes. Okay, so after third, your P3 comes. So it has 3 seconds remaining. P3 has 6 seconds remaining, and P4 has 5 seconds remaining. So which one will be chosen? Again, P2 will be chosen only because it has less seconds remaining, right? 3 seconds of work it's required. So P2 is completed completely. P2 is done. So after 6 seconds, which one will be scheduled? So you have two items here. You have your P1 in memory and P2, P3 in memory. So P3 has less time remaining, 6. So P3 will be scheduled. P3 will be scheduled. And at 8 second, P4 arrives. Right? At 8 second, P4 arrives. So P3 goes for 2 seconds. So 4 remaining. In this, now there are three candidates: P1, P3, and P4. P3 requires 4, P4 requires 5, and P1 requires 10. So chronologically, our concept is shortest remaining time. So P3 will be scheduled, and P3 will complete its 12 seconds. It's 4 seconds. So at P12, P3 will be completed. P3 will be completed. Okay, so let me. So P3 is done. Now the two remaining are P4 and P5. P1 and P4. P4 has obviously it's done. So P4 has obviously 5 seconds remaining and P1 has 10 seconds remaining. So P4 will be scheduled next for 5 seconds. 17 done. Then P1 remaining. P1 will be considered for 10 seconds. Right. So this will be the final result of the Canard chart. Right. So now we need to find out what is the average waiting time of each process. So let's calculate one by one the waiting times. For P1, what is the waiting time? So P1 waits for a total of P1 waits from this is the time P1 waits. Let me use different color for all of them. Let me use a different color. So P1 waits this time. So P1 waits from 2 to 17, that is 15 seconds, 15 ms. Now P2, what is the P2 wait time? P2 does not wait. P2 comes and just jumps into the work. So P2 comes and do this work from the time being. So P2 is 0 ms. Then comes P3. Then comes P3. P3 starts at 6. P3 starts at 6. Right. But P3 arrives at 3 seconds. So P3 arrives at 6 minus 3, that is 3 ms. So it waits for 3 ms. So it will be something like this, 3 to 6. Now P4. P4 arrives at 8 and it starts at 12. Before some place here it arrives and it goes to 12. So P4 waits for 12 minus 8 is equal to 4 nanoseconds, 4 ms, milliseconds. Right. So the total waiting time is, average waiting time is, average uh, your average wait time is 15 plus 0 plus 3 plus 4 divided by 4, that is 22 divided by 4, that is 4.5 that is 5.5 milliseconds. So the correct answer is 5.5 ms. So this is a quite typical question that comes in your exams, like what is the average waiting time? And this is not the only question that is asked. In many cases, you are asked average waiting time, average run time, and those kind of things. There are like this sort of question has many types. That's what I meant. Okay, so let's go to the next question. So you have been given a uniprocessor system executing three tasks T1, T2, T3, each of which is composed of an infinite sequence of jobs, which arrives periodically at 3, 7, and 20 milliseconds. So it arrives at 3, 7, and 20 milliseconds respectively. The priority of each task is inversely proportional to its period. It inverse of its period, and the available tasks are scheduled in the order of their priority, with the highest priority task first. Each instance of T1, T2, and T3 requires an execution time of 1 to 4 respectively. Given all tasks initially arrive at the beginning at first millisecond and task preempts are allowed, the first instance for the T3 completes execution. Okay, so think about it this way. So there are so here are the points. Let me write down. There are infinite number of T1, T2, and T3, right? And it arrive periodically at interval of 3, 7, and 20, right? So so they require each execution time of 1, 2, and 4, and priority of each task is inverse of its period. So priority of each task is inverse of its period. So uh, so this statement means priority of each task inverse of period is basically, what it means is smaller shortest job is fast, executed fast. Shortest job is executed fast. Like, so it is basically your shortest job first algorithm. So initially it says all the tasks arrive at the beginning at the first millisecond and task preemptions are allowed. So the first instance of T3 completes execution at dash milliseconds. So let's do it. Let's prepare the Gantt chart and do it. Okay, so let's do the Gantt chart. So initially, initially you have this. So T1 is 1, T2 is 4, T2 is 2, sorry, and T3 is 4. Okay, so this is the sequence, and this is the order of priority, the one with the list here, and they arrive regularly at an interval of 3, 7, and 20. 3, 7, and 20. T3 arrives. So initially all of them are present at the first time. So T1 is scheduled first because it is the shortest time. So T1 gets over at first instance of T1 is overs at this time. Then the shortest time after this is this two. So T2 is done for 2 seconds. T21 is done from 0 to 1 to 3 for 2 seconds. It's done. Now, now in the third second, T1 again arrives. So next 1 of T2, next session of T1 arrives. So it has the shortest time. So that one is scheduled first. So it is done. So 4 seconds. Now what is present in the memory? Sorry, this will be T1 2. So now is the now only T3 is present, and it requires 4 seconds, and the next one will come at T2 will come at yeah. So let's do that. So let me do it at what seconds this one will come. This is a little bit confusing. So T1 1 will T1 2 3 7 and 20. T2 will come at 3. T1 3 will come at 6. T1 4 will come at 9. T1 5 will come at 12. Similarly, T2 2 will come at 7. T2 3 will come at 14. T2 4 will come at 21, and T2 5 will come at 28. So, and this let continue. T1 6 will come at 15. T1 7 will come at 18. T1 8 will come at 19, and T1 9 sorry it's T1 7 will come at T1 6 will come at 21. T1 9 will come at 24. Okay, so in third second, which one is present? uh, T3 is present and T1 is present, but T1 gets done because it is arrived first. Now between 4 to 6 you have a free run of T3. So T3 1 is scheduled here between 4 to 6, and then it gets preempted because it has two left. It has two left, and T1 2 arrives, T1 3 arrives. So T1 3 is scheduled, and T1 3 is done at 7. Now T2 arrives, which has 2, and T2 gets the has the bigger priority because it has the smaller one. So T2 arrives 1. So T2 gets done. T2 uh, has a free run of up to 9. T2 2 is done. So T2 2 is done. T2 1 is done. T1 3 is done. Okay. So now between 2 seconds to 9 it is done. Now T1 4 arrives. T1 4 arrives and it takes 1 second. Then T1 4 arrives and T1 4 is done. Now at this point of time, T2 3 is not there. Now T3 can now go into the system and do his job. T3 1, T3 1. Right. So uh, sorry for this. So it is 12. So after 12 seconds, first instance of T3 is done. First instance of T3 is done. So the time required, so the first instance of T3 completes its execution in basically uh, 12 second. So 12 second is the correct answer. So correct answer is 12 seconds. Clear. So this is the order of priority we have seen, and this is the time required. And we know that the jobs arrive at an interval of 3, 7, and 20. So we defined each instance of the job here accordingly for T1, T2, and T3 at the time at which it arrives. Okay, and that is how you get the final answer. So this is again a very typical problem that comes for your scheduling kind of scenarios. So if you have any doubt, you can ask. These are all the questions I had. So any problem you have any doubt, you can ask regarding it. So I know these questions were a little bit difficult compared to what was done previously, but that's the point because I saw that multiple page tables. So these two are very typically hard questions. I know question one and question two, which dealt with your multi-level page table, three-level page table. Those are typically questions that are commonly asked also. But this concept was taught in the class of multi-level page table. So it's okay to have some questions regarding it. So these question one and two we discussed the multi-level page table. So one common trick what I will suggest always is that uh, last level basically holds the all the pages entry, right? So we saw that here 2 to the power 46 variables total number of pages, that is the total number of entries in T3. So that is one trick. And then all the page table entries of T2 which references uh, all the pages, so all entries of T2 references all the page tables of T3, total number of page tables that are there in T3. So and that way you do the back calculation and do it. Look, that was similarly similar here, uh, how it is done. So this was your normal question on your page replacement algorithms, LRU, FIFO, and optimal. We did the calculation. Then there was your page table access time a problem. So if there is a page fault, what happens and all. This was a problem on your partition. So what happens for you when you select a best case partition and all? Then there was this is another set of questions like after the page table one, this is another set of questions where you need to find out what is the size of each page table entry and all. And so here we found out that each page table entry is basically so each page table entry is basically stores your virtual memory address, your frame number. So your frame number is one of the entry in your page table entry as well as some other bits. And if you have to calculate the size of the entire page table entry, so each entire page table entry will contains all the pages references. So each page table entry into the number of frame size. That is the total size and all. This was also same. This was also same. Then this was a problem again on your page fault based. Two problems on your page fault based things. This was on your dig scheduling algorithm. So we did for STF save shortest remaining time fast and all shortest 6 time fast and FCFS demonstration of how it happens. Then a binary semaphore and everything. and last two was your own scheduling that previously we have covered. So thank you for joining. I hope you have a nice session. So if you have any doubt, you can ask or feel free to leave. Yeah. Thank you for best of luck for your exams.